Hello students, and welcome to today's notes, Flow of Logic. Starting off with deductive reasoning, a series of facts, definitions, and accepted properties in a logical order to form a logical argument is the basic definition here of deductive reasoning. I'll go a little bit further with identifying a kind of general to specific kind of flow of understanding, or at least how you perform an argument. That is a deductive reasoning argument. Inductive reasoning, which is much harder to do, goes from specific to general information. So the flow of logic goes in that particular order. Again, as opposed to deductive reasoning, where you're given general information and you go towards the specific. There are two laws of deductive reasoning. The law of detachment. If P then Q is a true statement and P is true, then Q is true. Symbolically, this is how we write it. So if P then Q is true, and we know P is already true, then Q must also be true. The law of syllogism, if P then Q and Q then R are both true, then P then R is true. So there's a connection here, as you can see in both statements, P then Q, Q then R. There's a connection, as you can see, in such a way where the conclusion of the first statement is the same as the hypothesis of the second statement. So P then R must be true. Okay. Let's take a look at the next example and kind of help frame our understanding a little bit different with some context. If it rains, then PE will be indoors. So if R, then I. If it rains, then we'll be indoors for PE. If PE is indoors, then we will play badminton. So if indoors, then badminton. If I, then B. Third, it is raining. So this is just a statement of truth. It is in fact raining. So by the law of syllogism, here's how we put things together. So R, then I, then B. Again, those are the first two. And then, of course, because I is the same here and here, the conclusion of one is the same as the hypothesis of the other. R implies B. Or we can say R, then B. Or you can say as a final answer, if it rains, then we will play badminton. And it is true. By the law of detachment, as you can see, these are the only two statements that we're going to utilize. If it rains, okay, then we play badminton. It's actually from the prior kind of flow of logic. And then we also incorporate the singular R, that it is raining, and that's true. And because this is the case, we can argue that B must also be true. So we will play badminton. Okay, if we continue, let's go ahead and take a look. It says equivalent statements. So in terms of what we saw back in section 1.4, now I will be very honest here. I might have to revisit that section title, just because we have different section titles possibly from the past years, but I'm going to rewrite that in a different manner and at a different time. But we have discussed certainly a conditional statement such that if P then Q is what we have, it's contrapositive. If you recall, contrapositive means you flip the two letters, the hypothesis and the conclusion, and you negate both. So again, a conditional statement, if P then Q, and it's contrapositive, not Q then not P, have the same truth value. Either both are true or both are false. Okay, so a conditional and it's contrapositive. Likewise, the converse, if Q then P, and the inverse, if not P then not Q, also have the same truth value. Either both are true. Okay, either both are true or both are false. And as a little note, it says the inverse is the contrapositive of the converse. I'll explain that as we go through. A lot of this language is a little bit more complicated without actually seeing an example. So let's go ahead and just continue, and we'll get into the examples. Again, another recollection that we can pull out from a prior section. I'll refine that later for you. A biconditional statement, P, then Q, which by the way has a double arrow on it, which technically reads in both directions. Okay, so a biconditional such that you see P then Q, but also in the other direction, if Q then P, we're going to use the language of if and only if. I wrote it down here, but you can also place it here if you'd like, because that's the first place you're seeing it. So if P then Q and if Q then P, both of those are true. And it is a single statement consisting of a conditional statement, P then Q, and its converse, Q then P, like I said. So if P then Q or P then Q, or Q then P, excuse me, is true, then so are the other two statements as individual statements. Well, P then Q, of course, like I already said, but also Q then P. I got to be very careful as I describe this with an if and only if. When I use if and only if, or IFF in the context of this type of situation, please note that I may use this depending upon the situation, or I may use that. Principles of contrapositives. In any logical argument, the contrapositive can replace its conditional statement without a loss of validity. So symbolically speaking, if P then Q, and then you've got an if and only if. So it's actually a neat connection to taking this statement but making it an if and only if, as you can see. In the next statement it says not Q, then not P. Okay. This is a different version of that form that we are going to utilize depending upon the situation. So you're going to find very quickly that if P then Q is not an effective way to continue your flow of logical arguments, then you're going to possibly use this. And notice this is just the essentially the contrapositive. In other words, flipping these two letters and changing them so that they're negated. So this is a not Q, then not P. Principles of biconditionals. In any logical argument, a biconditional can be replaced by either its conditional statement or its converse without a loss of validity. So again, here's the if and only if premise. Again, we can rewrite this as P then Q, or we can write it as Q then P. Okay, so as we can see here at the bottom, I've got some examples for us to take a look at. They're not particularly difficult, but I want to make very careful work here. I want to make sure as I do my careful work that we're on track with what these statements entail and what you can do with them. So what I do first is I number all of my statements. I have 4 statements. The first statement is a biconditional, and again, like we saw up above, it reads as if R then P, but also if P then R. Both of those directions are true. So for the first step, as you can see here, what I've done is I've taken the statement and I've flipped it. Okay. Now I actually also included the arrows in both directions, which technically I didn't have to do, but the reason I at least flipped it, again, this is okay to write, is because I noticed that in the third statement, look at what I have as my hypothesis. My hypothesis is R. So if you recall, we're trying to match these letters, and I've done that. Okay, I flipped the first statement correctly because it's true still, and I've left the third statement. I've numbered them for you. I've left it there such that these two letters are the same. This is precisely, again, if you reflect back on the law of syllogism, this is precisely what the law of syllogism is calling for. So we can now say P, then not S, which is this conclusion. So I've kind of branched things off in such a way where you can see these two paired up, leading to now this statement. Okay, the next goal should be to see where you can find a not S in a hypothesis. So it looks like step 4 or statement 4 is going to get us there. At least I wrote it there. But how the heck did I go from if T then S to not S then not T? Remember that we can take this statement and we can rewrite it accordingly. We can flip it, and notice we can negate it. If you flip it and you negate it, it's technically true. It's this statement flipped and negated, in other words, the contrapositive that we're utilizing. So look, we've got not S, I circled it, not S, I circled that. P, then not T is the conclusion on that step. Now we look at the not T. All right, what have we not yet used? Well, we haven't used statement number 2. Statement number 2, okay, which maybe I'll do like this for you. To turn this statement into one where it has not T as the hypothesis, you'd flip, right? So not T, then not Q. This is how I then, as you can see right here, how I rewrote it such that what, not T, then not Q. These two letters are the same. Circle those, please. And then your final answer. Here's your hypothesis that remains, and here's your conclusion that remains. So if P, then not Q. And that's your final answer. Number 2. I'm going to actually ask that, well, I'll tell you what, with the time I have, I can do number 2. And I hope we can get to the last question. I changed it out and made it a third problem, technically, not the second one. So anyways, so the first statement, second, third, and fourth, I just rewrote. You're oftentimes, folks, going to nicely be able to use the biconditional on most questions to start with, which I did here. And I did flip it. And look, I didn't use the double arrow. I only used the single arrow because, as it turns out, I want to use D, as I noticed down here in statement 4. I want to use D again. So D here and D there. These are the same. I paired them up. So B, then E is the conclusion. Okay, let's keep pairing things up. Actually, as it turns out, I don't have an E, nor do I have a B, just in any of the statements that I see. Or technically, if you notice that statement number 2 does, but it's not in the position we necessarily want. So, and actually what I could have done, now that I reflect back, I could have just popped this second statement right here, and that would have been just as effective. There's a lot of different ways you can do this, but I'm going to finish it as I did it. Anyways, as I did it, I took B then E, and I took its contrapositive. And you remember, you can do this. So B then E, this right here is the contrapositive, so not E, then not B. Now I want not B. Here I want not B, which technically I also did using the contrapositive. So I did a little bit of an extra step, which is fine. So in other words, not B, then not A. So take this, and obviously that's what you see as its contrapositive. These two letters are the same, and because they're the same, not E implies not A. So our conclusion on that step then is not E implies not A. Again, we still have what? Step 3 or argument 3 to utilize. So we plug that in here. Nicely enough, I set ourselves up for not A. They are the same. So your final answer, noting that hypothesis and that conclusion, not A, then C. Or not E, pardon. Not E, then C. This example is pretty nice. It shows here an animal is a marsupial if and only if it has a pouch. My aunt's pet is a kangaroo, and kangaroos have pouches. So what I've written here is M, if and only if P, A implies K, and K implies P. Here I've paired up 1 and 3. The P's here and here I can pair up quite nicely. Notice I also flipped. If M implies P, P also implies M, so I can flip it like so. It's a biconditional again, right? If and only if. These numbers or letters, excuse me, are the same. So K must imply M in the next step. I haven't yet used statement 2, so pop that in right there. These two letters are the same, and because of the same, A implies M. So if A implies M as your final conclusion in that particular flow of logic, the statement that you would make, which is a nice culmination, kind of contextually speaking, in your understanding, I hope is all coming together on this now. If my aunt has a pet, so aunt, if my aunt, A, remember, is aunt, if my aunt A has a pet, then it's a marsupial, the letter M.